Hello and welcome back to this course on discrete mathematics, and today we are going to look at this part 3 of graph theory, and generally we are going to talk about cycles, and also I will introduce trees, and in trees we are going to talk about the minimum spanning tree. So in the previous lecture we talked about paths and cycle, so that's where we are going to begin with. Let's talk more about this cycles partitioned into simple cycle. So here is the claim that we have: if every vertex is of even degree, then the edge can be partitioned into simple cycles. First we can find out, let's see whether we have one cycle by the same idea as before. Let's start from any vertex, go to unvisited edges as long as possible. So what we are going to do is that you are going to start from one vertex we are trying to start traversing and go to unvisited edges as long as possible in a graph. So here is one of a sample graphs available. So we have 8 vertices there, and as you move forward from one vertex to the other one, we cannot get struck before we get a cycle. But unfortunately here, we have already finished connected with all the vertex, but at this point here, that's where the cycle is formed. So that part, that is what the cycle is, the representation of the cycle is. Well, now we have to determine how we can in fact partition different simple cycle. So if every vertex of an even degree, then edge can be partitioned into simple cycle. So here you can see there are again around 10 vertices, and you have lots of edges that are connecting these vertices. And since we have these connections, in fact you can visualize there are a lot of different cycles being formed, or the loop is being formed. Let's take one at a time. How about this one? Did you see that these 5 vertices are connected and a simple cycle is preserved there? Yes, you can in fact partition this simple cycle from this graph. Take it out. Yeah, you have actually taken out this graph. Next, do you find any other cycles? Yes, in fact you can see that there is another cycle there that connects all these 4 vertices. Take that out. Well then, now we still have some cycles left. Let's go ahead and see how this 5 vertices are connected together to form another cycle. Let's take this and put aside. Still it seems that there are a few more simple cycles are available. Let's take it out. Here is the last one. Yes. So what we have done here is that we have just partitioned these simple cycles from the original graph that is given to us. Yes, if every vertex is of even degree, then the edge can be partitioned into simple cycle. That's the actual claim. And let's see the simple cycle, and we are to remove the edge from C, from the graph G, and call now the new graph G. So as we have seen in the previous example, we are trying to remove the edge from C there. So the degree of each vertex is either unchanged or decreased by 2 when you remove that. Yeah. So every vertex of a graph G dash is still even degree, the new graph. is still even degree. Note that G dash has fewer edges than G, definitely, yeah, because the original graph has more edge than the graph that you just taken out. So by induction, G dash can be partitioned into the simple cycles C1, C2, Ck. Right. So we have shown an example in which we try to partition the given graph into many simple partitioned cycles. So the original graph G can be partitioned into simple cycles C1, C2 till Ck. Again, the proof. We have informally proved the following claims, like claim 1, if the edge has connected graph can be partitioned into simple graph, right? So if the edge has the connected graph, it can be partitioned into simple graph, then we can construct an Eulerian cycle. We have done that in the previous lecture. If the vertex of even degree, then edge can be partitioned into cycles. The Euler's theorem basically states the same. A connected graph has an Eulerian cycle if and only if every vertex is of even degree. That's where we started off, the Eulerian theorem. Trees. This is one of the important topics under graph theory. Graphs with no cycle can be considered as tree. As you can see here, all these vertices, they are connected by means of edges, but it does not form a cycle. Moreover, a connected graph with no cycles can be also represented by means of the one below here. So since it looks like a tree, and in fact it seems as if in most cases we have the tree has the root at the bottom and the leaves at the top, but in trees that we are going to deal with, in all the cases we have the root at the top and the leaf at the bottom. So there is an example where we have a lot of connections. So this when you have more trees connected together, we call that as forest. So let's see more on trees. A leaf is a vertex of degree 1. In other words, that is kind of a last part, because all other vertices except these two vertices, all other vertices they have degree 2, but only this last two vertices has the degree of 1. So we call that as a leaf. This is another example of leaves. You can see these are the leaves, and again there are a lot more leaves here. All these are leaves. The one that appears at the bottom or the end. Again, more parts of this tree properties. You can see the U and V are the vertices at the end. A tree is connected graph with no cycle. That is one of the basic definition of trees. Can there be no path between U and V? No, it's not possible. Can there be more than one simple path between U and V? You can see here, this is another way to express it, but the question is, will it create a cycle? If this creates a cycle, then the property of tree is gone there. So you can't have more than one simple path between U and V. Again, the claim, in a tree there is a unique simple path between every pair of vertices. A unique simple path between every pair of vertices that you have. Well, we still go by the definition of the tree, that is a connected graph with no cycles. The question is, can a tree has no leaves? Is it possible? Then every vertex has a degree at least 2, which means that that is not possible, right? So go to an unvisited edge as long as possible. You are trying to go to an unvisited edge, and then in the end the tree is the place where you cannot get struck. So if you get struck there, then this is not a tree. So once you get struck like this, this forms a cycle. So in this case it cannot. Yes, a tree has leaves. So can a tree has no leaves? No, it cannot. It should have leaves. Then how many edges does the tree have? Well, we have seen different examples of tree, and there are different ways to express a tree. So we usually have n to denote the number of vertices and m to denote the number of edges in a graph. So number of edges in a tree should be n minus 1. In other words, at least 1 less than the number of vertices. So we have seen many examples of it. So you can consider each and every example of tree. For example, even this one here, you have how many vertices here? Say you have 1, 2, 3, 4, 5. You have 5 vertices, but how many edges are there? It's only 4, right? You have 1, 2, 3, 4 vertices are there. So it's simple task of calculating how many edges does a tree have? 1 less than the number of vertices, or in other words n minus 1, where n is the number of vertices. Look at a leaf V here. Is T of V a tree? Well, now you have to ask this question. Can this has a cycle? Is this a connected one? No, definitely it's not it's not a cycle, and you can see they are connected by means of these 2 other vertices that you are introducing here. Yes, this is in fact a tree, and with n minus 1 minus 1 equals n minus 2 edges. So that's with n minus 2 parts there. So this tree has n minus 1 edges. More properties of tree is given here. A graph is a tree if and only if there is a unique simple path between every pair of vertices. This is the definition we have seen earlier as well. So this is characterized by the edges. So there are 2 characteristics. One is characterized by the path, in which we are saying that there is a unique path between every pair of vertices, and then there is another characterizations by the edges. A graph is a tree if and only if it is connected and has n minus 1 edges, where n is the number of vertices. Let's go on to this rooted tree. A rooted tree is a directed graph which has one vertex, say V0, called the root, and has no arc coming into it. So V0 equals 0. So every other vertices, the tree has only one path to form it. So Vi is only 1. So there may be any number of path from any vertex. So this is the rooted tree in which we have this following definition for the tree. It is essential for us to understand these definition as we move on to this discussion of tree. To starting with, all the vertices located n edges from V0 are said to be at level n. So we will consider one by one. Let's look at this part: parent, child, sibling, descendant, height, leaves, and the level. In fact, we have to consider these things one by one. So all the vertices located n edges from V0 are said to be at n level. In other words, it depends upon the number of edges from V0. And next definition is, a vertex V is considered the parent of all of the vertices connected to it by edges leaving V. We will talk about this in detail. If I show you a graph, you would easy to understand. It will be easy for you to understand what it is. As you have the parent vertex and they are connected to the next level to its child. A vertex V is considered the child if the vertex connected to a single edge entering. So the edges for the parent, there should be at least one edge leaving. This is for the parent. And for the child, there should be at least one edge entering. This is the child. A vertex V is considered as sibling of all vertices at the same level with the same parent. So this is here. This is a sibling. The same parent, but at the same level of C you have. Vertex V of J is considered descendant of a vertex Vi if there is a path from Vi to Vj. Yes, if there is a path that you have from Vi to Vj, then this is considered to be the descendant of vertex Vi. So in this example, if you consider this as the vertex Vi, and if this is, in fact we made it as C, but if you consider Vj, then here Vj is considered as descendant of Vi if there is a path. Yes, when you establish a path, we can consider this as a descendant. The height of a tree is the number of the largest level. Say for example, you have another level here and another one. So you have level 1, 2, 3 in different cases. So that would be the height. The vertex of a tree that has no children is called leaf. So for example, this part has no children, so these are called leaves. Let's consider some ways to see it. For example, V0 is the parent of V1, V2, V3, V4, and V1, V2, V3, V4 are the children of V0. V1, V2, V3 and V4 are the siblings. V5, V6, V7, V8 are the leaves because it has no children, and the height of the tree is 2. We can see from here level 1 and level 2 is the height. So if every vertex of a tree has at most n children, then the tree is considered n tree. And if every vertex of a tree with offspring has exactly n offspring, then they are kind of called as complete n tree, because every offspring has n offspring. Every vertex of a tree with n offspring has exactly n offspring. and when n is 2 we call this as binary, because everywhere you have 2, 2, 2 coming out, something similar to the one which has been shown here. Everything has 2. And just to explain this further, if you want to have everything has 2, something like this, right? So that's like a so-called a complete n tree, and if it's n is 2, in our case we have this as binary tree. Then comes this definition of the spanning tree. T is a spanning tree of G if T is a tree with the same vertex as G and A subset of edge of G. Let's consider what it is in general. So the weighted graph, we consider the weighted graph. A weighted graph is a graph whose edge has an associated real number weight. So for example, you have these edges between A and B has the weight 30, edges between B and C has the weight 10, edges between A and C has the weight 15. So weight of the edge AB is called the distance between AB. You can consider it as the distance. Okay, so two vertices are neighbors if they are connected by an edge. So you could say that the neighbors of A is B and C, neighbors of D is C, neighbors of C is D, neighbors of say B is A and C. So likewise you can consider the neighbors of C is B, A and D. Yes, the two vertices are adjacent if they are neighbors. If they are neighbors, then they are adjacent to one another. The nearest neighbor of a vertex is the neighbor with the smallest weight. So the nearest neighbor is the one which has smallest weight. Say for example, the vertex C has 3 neighbors, A, B and D, but you could say D is the nearest neighbor because it has the smallest weight. Minimal spanning tree. So here is this part where we are asked to find the minimum spanning tree, because a spanning tree is, generally speaking, it produced by means of these given weights for us. A minimum spanning tree is a spanning tree for which the sum of weights of all edges is as small as possible. For example, with the same given problem that we had, you can connect all these 4 vertices with the given edges, and you can sum up all these weights. And as you notice here, the way to connect these 4 vertices might vary, and eventually your weights also varies, 32, 47, 52, so on. So the question about minimum spanning tree is that if it has the minimum value among this spanning trees, because this one is a spanning tree, this is another spanning tree, this is another spanning tree, all are spanning tree out of this given tree. This is the given tree for us, and from this we are developing different spanning tree. The minimal spanning tree is the one which has the smallest possible weight. When you add all these together, sum of the weight should be smallest, which means that it clearly shows that among this is the smallest, or in other words, this one is the minimal spanning tree of the given tree. So as we talk about this minimal spanning tree, I want to give you one more example on how this can be very efficient. For example, you consider you have a electric power grid, and from this electric power grid you are going to supply this power to different houses. Say for example, you have different houses. You are supplying the power. So these are different houses. Well, the electricity has been supplied to all these things from this power corporation, and you can notice that it's kind of an inefficient way of connecting all these houses. So that's one of the application of minimum spanning tree, where you can in fact model it more efficiently and connect it all together. Say for example, you can consider this way. Instead of having it like this, you can always go ahead and try to this, for example. Yes, this is one of the efficient way of connecting it. So that's where one of the applications of the spanning tree would come up, so that we minimize the cost or the distance. So the main objective is to minimize the cost or the distance, so that things can be done more efficiently. There's a minimum spanning tree. Once you know the network, once you know the actual trees, you can try to form which is the best minimal spanning tree. And once you come up with this minimal spanning tree, yes, you can apply it mathematically so that it can be very useful for various real world application. So as the continuation of this lecture, we are going to see the applications. There are a lot of algorithms in graph theory which are very useful. We will talk about the adjacency matrix, and then we talk about some basic algorithms that defines us finding the minimum cost and also the shortest path. I am looking forward to meet you in the next lecture with all those informations of applications of graph theory. Until I catch you there, have a good time and goodbye.